Hi everyone, this is Purnima Mahalingam and we are watching video lecture series on solar and wind energy. Today we are going to discuss the topic about polytronics, which is enabling the modeling wind energy systems. Okay. So polytronics are crucial for modern wind energy systems. We know that they ensures the efficient grid integrations and optimize energy capturings, and these technologies improves annual energy production stability significations, and it is essential for managing a variable wind output. This is an overall view of this topic. Come, let's go into the topic. Here, first of all, we are seeing what is the main role of polytronics in wind energy systems. Here we have so many roles. First one is variable wind speed. So here first thing is wind speed fluctuates frequencies and power electronics adapt to these rapid change. This ensures the continuous power generations. This is the first one is variable wind speed and grid code compliance. So precious control is necessary for grid stability. Grid stability plays a vital roles, and polytronics maintain exact frequencies and voltage. So frequency matching is very important for grid connections. Grid frequency matching, this meets strict grid requirement. Okay, next one is maximum power capturing technologies. Some maximum power capturing technologies, that is MPPT technologies, which optimize energies and energy extraction. It captures the maximum powers at variable wind speed. This boosts the overall efficiency. And finally, next one is enhancing grid supports. So polytronics provide critical grid services. They offers reactive power that fault rate through this strengths are grid resilience. So these are the main four important roles of polytronics in wind energy. One is wind speed, variable wind speed. Next one is grid code compiler. Next one is maximum power captures, and next one is enhanced grid supports. These are the main four main roles. The next one is core component of what are the core component, the building blocks of control. So here we have main four component. One is AC to DC rectifiers. The next one is DC to AC inverters, semiconductors, and control systems. So here we have seen already um, so many things. Sorry. So first one is a DC to AC to DC rectifier. This converts the AC supply to the DC supply. And first, they're the first steps in power conditioning. And next was DC to AC. This grid compiling AC, and this synchronized with the electrical grid. The next one is semiconductors. Semiconductors, the ICBT, they are key switch components. They operate at high frequency. This enables the efficient power conversions. Okay. Next one is control system. This is the main thing. So DSP, this DSP preciously managed power flows. They optimize interactions with the grid, and these systems are brain of the operation. So control is the brain of the operations. These are the main four blocks of building blocks of control. Okay, now coming to next, what type of topologies we have using. So we have using main. One is double field induction generator, DFIJ topology. What do you mean by DFIJ systems? Are partially scale converter. That is main important. This is a partial scale converter. This converts handles 25 to 30% of the turbine powers. It is offer cost effective of wind energies. Okay, the rotor side converter RSC controls active and reactive power. It manage the rotor current for optimized performance. The performances, and the grid side converter regulates the DC link voltage. It is also provided grid support converges. So this is what an and DFIG topologies. So next one is full scale converter. So full scale converter topologies. What is a full scale converter topology? Here it is. It is 100% converter rating. The full scale, it is 100% converter rating. All generated power passes through the electronics. They provide comprehensive control. So next one is direct drive or geared. So full scale converter is compatible with various generators. It supports both PMSG is a permanent magnet synchronous generation and induction generator. So enhancing grid control and dominates off source. So these are the main 4 points of full scale converters. Now coming to challenges and innovations, what are the challenges? And based on harmonic distortions, grid interferences and equipment is stressed. It is stressed, and advanced filtering and multi-level converters in a full-scale converters. The reliability is increased downtime and maintenance cost, and robust component selections and predictive maintenance. Predictive maintenance is important. And next is thermal management. Based on thermal management, so efficiency loss is high at the liquid cooling system, so optimal airflow. The next is cost versus performance, is a high initial investment, standardization, volume manufacturing, and performance gained. So these are the challenges and innovations. And finally, what are the future trends? So wide bandgap semiconductor. First one is wide bandgap semiconductors and silicon and germanium nitrates and multi-level converters. We have multi-level converters and HVDC offshores and grid forming inverters. These are the future trends in wind power electronics. Finally, we are coming to the conclusions of power electronics. One is essence for grid interactions. So main thing, first one is essence for grid interactions, integrations, and maximum energy captures. Energy capture is maximize and enable large and more efficient turbine. Enables large and more efficient turbine, and finally drives future grid stability. These are the conclusions. I hope today you understand something about power electronics and wind energies, and we will meet you next videos. Thank you so much for watching. Thank you.